Welcome to the third module of DSP RTL design video series. Hi, I am Gyan, and in this video I will guide you through the system Verilog design and test bench development of a multiplier. Let's get started. This module is written in system Verilog and I will walk you through the theory behind it, the design choices and how the code works step by step. Let's first understand the top level features of this module. So, this module handles multiplications of a signed number with an unsigned number. It is a fully synchronous design and we can have the parameterized input factors of the multiplier. The design is very efficient for hardware implementation and rather I would say it is a hardware optimized design. So now let's first understand the type of parameters with which we are using here and the input output ports of this module. So here we have two parameters, factor 1 width and factor 2 width. These are the width for the two inputs of the multiplier. And then, like any other synchronous design, we have the two important input ports, which are clock and reset, and two inputs for the multiplier, which are factor 1 and factor 2 with parameterized width. And then we have our output product. The width of the output product is the combined width of two input factors. Now, we have some internal signals defined for this module, which are the first one is the unsigned product, and the next is unsigned factor 1, and the next variable or the next signal internal signal is the sign bit of factor 1. So if you see here, our input factor 1 is signed number and our input factor 2 is a unsigned number. So this multiplier basically works for the inputs where one input is signed and the another input is unsigned. In many DSP applications, we have such a arithmetic where few of our variables would be signed and few of our variables would be unsigned, and we have to multiply them and get a output signed product. So how do we handle this kind of multiplication is what we are going to understand in this module. Okay, so this is very important. The next equation is very important, and what we are doing here is we are converting our signed input factor 1 to a unsigned value if our input is negative. Okay, so let's say our input factor 1 value is minus 5. So what we would do, we would convert it to plus 5. Okay, and our second input to the multiplier, which is factor 2, is anyway a unsigned value. So, and for an example, let's say that our input factor 2 value is plus 5. So now we will convert our input factor 1, which was minus 5, to 5, and then we will multiply it with the another factor which is 5, and we will get our multiplication plus 25. But that is actually wrong. We should get a minus 25. So what we would do, we would do again some kind of signed arithmetic to convert it into minus 25. Okay, so let's understand it step by step. So this is our first step, and in this first step what we are doing, if our input factor 1 is negative, what we do, we take 2's complement of this number to convert it to a unsigned value, and then if our number is positive only, then we don't do anything. Our unsigned factor 1 is nothing but input factor 1. So this is the first expression. Now here is the actual product happens in the hardware. So this is where the hardware multiplier is realized, and on every positive edge of clock we kind of execute this hardware, and whenever there is a active low reset, we reset our unsigned product to 0, and we also assign our sign of the factor 1 to 0. Else what we do, we our unsigned product would be unsigned factor 1 multiplied by the input factor 2. and here we register the sign bit of our first signed input, which is factor 1. So the MSB of I factor 1 actually indicates the sign of the I factor 1. So now we know, so now basically what we have done, we have converted the multiplications, or we have uh, actually evaluated the multiplication expression in terms of unsigned numbers, and also we have stored the kind of, or we have registered the information of sign bit of our signed input factor. Now, depending on the sign of our signed number input number, which is IFAC1, what we would do, if our input factor 1 was negative, we again take the 2's complement of our unsigned product. So like I said, we will convert plus 25 into minus 25 here. Otherwise, if both the numbers, the first number was also positive, anyway the second number is a unsigned number, so its range starts from 0 to positive direction. If both the numbers are positive, we don't do anything, and our output product would be nothing but our internal calculated unsigned product itself. So this is how these kind of multipliers can be implemented in hardware, where we have the kind of mixed arithmetic, where one number is signed and another number is unsigned. Similarly, this can also be extended for other kind of arithmetics, like if both the numbers are unsigned, if both the numbers are signed, all those combinations can be implemented with some updates in the design. So I have listed few of the applications, and very important applications where these kind of designs can be used. So one of the applications would be in ADC systems, where we have information like the ADC samples data, which we sample and convert into digital form, and that form is basically a signed representation. So the ADC samples are signed, and then for the gain error correction, basically we multiply by gain and do the subtractions with the offset. So sometimes the gains are positive and the input, another the ADC samples are kind of signed. So we have to multiply the signed numbers with an unsigned number, and in those kind of applications we can implement the logic like this. Well, the applications are wide in the DSP domain, and these kind of operations can be used in digital filters, FFT, inverse FFT cores, um, as I said, ADC modulators, demodulators, neural networks, the multiply and accumulate blocks, audio video processing, high speed DSP data path, which requires the mixed signal arithmetic. So hope this is clear. It is a small concept but very important how we deal with the signed numbers. Now let's understand and go through the test based development of this module, and we will see how we can verify these kind of designs. So the DSP multiplier TB is the top level module name for this for the test bench of this module. We have the variable input factor width, and here we are actually deriving the expression to find out the maximum value, the factor 1, which is here we are considering as a signed number. uh, what is the maximum and minimum values we can derive on the uh, signed input of the multiplier. Then we have the DUT input output ports, as well as the TB internal variables to calculate the reference value, which we will compare with the DUT output values. Then we have our DUT instantiated here. The DUT multiplier is instantiated here, and here we generate the clock for the DUT, and then we initialize the DUT input ports as well as the internal test bench variables. And this is the main task, which will actually drive the stimulus to the DUT and will compare the results, the DUT output results with our TB generated reference values. So now first understand what we are doing here in apply stimulus and checker task. So this is the apply stimulus and checker task, and here we generate the random value for the input factor 1 between the minimum value and max value of it. Then the second input, which is factor 2 of the multiplier, we generate a unsigned random value for that. And for the timing control or the synchronization between between the TB and the DUT, we use the positive edge of the clock as a, timing control um, activity or timing control event to make all the necessary checks and drive and basically kind of we are here doing the necessary checks, and we are checking if our duty output is matching our TB generated reference values. So when we apply the new input values to the duty, we get our at the next positive clock edge we get our new product value. So this is the this product value is the output from the DUT. If it is not equal to product ref, which we are deriving from our DUT, our TB itself, if they are not matching, then definitely there is a mismatch between the DUT generated product and the TB generated product, and we generate or we kind of increment our error count here. Here we are displaying what is the input values of factor 1 and factor 2, which we are driving to the DUT, and what is the reference and the DUT output product. And this is very important how we are generating the reference variable or the reference value in the DUT. So if you see here, there is one important point to note here. So here we are, our main goal is to multiply factor 1 with factor 2, but the point here is factor 1 is signed and factor 2 is unsigned, so we are multiplying the signed number with an unsigned number. So whenever so the width of our product ref is the combined width of factor 1 and factor 2, right? So what happens is, if we do not extend our factor 1, so kind of if we do not extend our factor 1 to the max value of product ref, then we won't get the expected result, because the other bits might get appended with 0. That would be wrong for a negative FAC1 or for a negative value of factor 1. So this is important concept. We have to sign extend our factor 1 to the full width of product ref before multiplying it with the unsigned factor 2 value. So this is how we have to multiply both the factor 1 and factor 2. Now this kind of sign extension we are not doing here in our DUT, right? So why we are not doing here is because we are converting our factor 1 to unsigned value before we do the multiplication in the DUT. So that is what we are doing here, and let me show you where exactly we are doing it. So if you see here, if our number is negative, then what we do, we take the 2's complement of our factor 1. So in this case we are kind of multiplying both unsigned number. So our product here is unsigned product. So either we can do this kind of thing in TB, or if we don't do, and if we want to directly multiply the two numbers, we have to sign extend our signed number to the full width of the product, and then we can multiply it easily and we will get the expected result. Now let's simulate this design. So I have selected the Siemens Quista for the simulation, and let me give a run here. So now let's understand the logs for the simulation. So the simulation started at time 0, and our first value is minus 5, factor 1 value is minus 5, and factor 2 value is 6. So the result we would get is 30. But this 30 we will get at the next rising edge of the clock, right? So at present rising edge, since in at the point of initialization